Hi students, welcome to DARASA Online. My name is Naftal Lucas Makumbire. I'm teaching chemistry, and today I want to present to you the topic of acids, bases, and salts. And the subtopic that I'm going to focus today will be the buffer solution. So this is what you're going to discuss today about the buffer solutions. Now, my students, by the end of this lesson, I'm sure that you'll be able to apply the principles of science and technology in carrying out different scientific investigations and analysis. This presentation is also very important because it contains some problems which involve calculations, but also others need you to explain. And I'm sure that you will be confident and you're going to be competent in solving different problems following this presentation. So I would like to take this opportunity to welcome you to watch this program till the end. And we are going to see also how different problems are solved in this particular presentation. So you are warmly welcome, my dear students. As I said to you that today we are going to discuss about the buffer solution from this topic of acid, bases, and salts. Now, before we go further, it is important for us to understand the definitions of some terms. It is very important. Now, if I ask you to define the buffer solutions, what are you going to say? What is all about buffer solution? Can you state it? Yes, it is very simple. I hope that you have studied this in the class. When we talk about buffer solution, buffer solutions, these are solutions Yes, buffer solutions, these are solutions which resist change in pH on addition of small amount of strong acid or strong base. This is the definition. So these solutions, they resist the change in pH, provided that the buffer capacity is not exceeded. When we talk about buffer capacity, I'm sure that you can be able to tell what is it all about. It is the amount of the acid or the base a buffer solution can take without having a significant change in the pH. So this is the introduction about the buffer solution. And I'm sure that you have studied this in the class, so it is very simple for you to understand these very simple informations. Now, from there, we have the two types of buffer solutions that you have studied even in the class. These two types of buffer solution are such as acidic buffer solution and a basic buffer solution. These are the two types of buffer solutions that we have. Let us discuss one after another in brief, and to come and see the selection of good buffer mixture for each particular part. But specifically today, we are going to deal with acidic buffer solution. So when you talk about acidic buffer solution, what are the solutions all about? Now, acidic buffer solution these are buffer solution with the pH less than 7. This is all about acidic buffer solution. And when we talk about basic buffer solution, with the pH greater than 7. Do you know about the pH scale? It is important for you to know about pH scale so that you can understand when you talk about pH less than 7, pH greater than 7. The pH scale is the scale of numbers ranging from 0 to 14, which show the degree of acidity, neutrality, and alkalinity. So it is very simple. Now, when the pH of the solution is less than 7, we say that that is acidic buffer solution. But when the pH is greater than 7, we say that that buffer solution is basic. If we have this illustration here on the board, so the pH which is less than 7, that means 7 to 0. Here we are talking about acidic. And when you look at the pH from 8 to 14 here, that means greater than 7. Here we are talking about the basic. So this is the pH scale. As you can see, here this 7 indicates neutral. So when the buffer solution is less than 7, that means this number here, we say that the buffer solution is acidic. And when the solution is having the pH greater than 7 up to 14, we say that that buffer solution is basic. So it is very simple for you to explain about the definition of those terms. Now, because our focus today is to deal with the acidic buffer solution, there are two things that we have to consider when we talk about the acidic buffer solution components. Now, number one, a good buffer mixture should have about equal concentration of its component. That is number one. And number two, the weaker acid and its strong salt, in order for them to be used as a buffer, should have the pH less than 7. So those are the two things to consider when you talk about a good buffer mixture. Now, acidic buffer solution can be prepared from the weak acid and the strong salt of that weak acid. This is how we prepare the acidic buffer solution. We take the weak acid and automatically these are always organic acid. They are weak. And the strong acid, the strong salt of that acid. We can have some examples here. Number one, acetic acid mixed with acetic acid, sodium acetate. This one is an example of the acidic buffer solution. So you can see acetic acid is weak, but sodium acetate, which is the strong salt of this acid, when mixed together, they make acidic buffer solution. So by writing, you can have this one. That one, by writing the chemical formula of these two compounds. So this is one of the examples of acidic buffer solution. And also, the second example, hydrogen cyanide and sodium cyanide. This is the weak acid and this is the strong salt of this acid. So when the two are mixed, they form acidic buffer solution. So it is very simple, as you can see. So these are the examples of the acidic buffer solution. So in general, can you say that acidic buffer solution are made by mixing the weak acid and the strong salt of that acid. So that is very simple to understand. Now, after we have discussed about the acidic buffer solution in short, I can ask you the question, why is it called acidic buffer solution? It is acidic. For example, when we take this one, acetic acid and sodium acetate, this is acidic buffer solution because the ionization constant for the acetic acid is greater than the ionization constant for this conjugate base. So when you compare, the ionization constant for this acid is greater than the ionization constant for the base. So this one makes this mixture to be acidic. So it is very simple from there. Now, my dear student, the question comes how the acidic buffer solution works. Or in other words, we say about the mechanism of acidic buffer solution. Now let us consider this buffer system, which consists of acetic acid and sodium acetate. Now, by considering this system, before addition of any salt, we have this acetic acid, which is the weak acid, first dissociates in the aqueous solution to produce few ions. But the dissociation of this weak acid is only partial. That means it gives very small amount of the ions in the solution because it is weak. Now, when this weak acid, which is acetic acid, dissociates partially, it gives the acetate ions and hydrogen ions. But these ions which are produced are very few. So here we have the equilibrium. These ions are in equilibrium with the acid. That is number one. It is important to consider this equilibrium because each component of the buffer has got its rule. So later I'm going to ask you what is the rule of the acid in the buffer system. So this is number one. Now after these partial dissociations of the acetic acid, the strong salt, which is this one, sodium acetate, will also dissociate in the solution. But the dissociation of this salt is complete. Why? Because this is the strong salt. Will dissociate completely to give acetate ions and sodium ions. Now, after this acetate ions is released in the solution from the strong salt, sorry, this is sodium acetate. After these ions are produced by this strong salt, here the acetate ions will disturb the concentration of the acetate ion in the solution. Why? Because already the acetate ions were present in the solution. But addition of these ones will disturb the equilibrium. If you remember, I told you that there is equilibrium, and as you can see, there is equilibrium here. So if that happens, it means that these concentrations which are produced by the strong salt will disturb the equilibrium. And I hope that you have the knowledge of Lakatyler's principle, that when one of the conditions changes, the position of equilibrium will shift in such a way that to eliminate the changes. So what will happen is that the acetate ions will combine with some hydrogen ions to form back the acetic acid in order to establish a new equilibrium. Now, if that happens, the few hydrogen ions that will remain after a new equilibrium is established are the ones that will determine the pH of the solution. So in that way, the pH of the solution will remain fairly constant because of the concentration of hydrogen ion will also remain fairly constant. So from here, the acetate ions will combine with these ones to give back the acetic acid. So that is number one. So in that way, you can see that the concentration of hydrogen ion is fairly kept constant. And if it is fairly kept constant because of the equilibrium position to shift in order to balance the change, therefore the pH of the solution is also remaining fairly constant. That is very, very important for you to understand. Now the second question comes. This is the system. It is already in the equilibrium. Now the question comes, when an acid is added to that buffer mixture, what will happen? That is the question. Now coming to discuss that question, yes, what will happen if a little acid is added? This little acid is hydrochloric acid, which is a strong acid, is added to this buffer system here. What will happen? Remember, initially we have this system. Acetic acid will ionize partially to give the acetate ions and hydrogen ions. And also the sodium acetate will ionize completely to produce the acetate ions and the sodium ions. Now from there, what happens if hydrochloric acid is added? Hydrochloric acid is a strong acid. This one will also ionize completely to produce hydrogen ion and chloride ion. Now what will happen here after that one? This hydrogen ion, which will be released from the strong acid, will increase the concentrations of hydrogen ion in the solution. So the dissociations of this strong acid releases hydrogen ions. This disturbs the concentration of hydrogen in the solution. So what will happen is when the concentration of hydrogen ion is increasing the solution, that means the pH will be lowered. Now, in order to prevent that lowering of the pH, the acetate ions from the strong salt will be enough to combine with hydrogen ions from the strong acid to form back the acetic acid. That means the equilibrium of the acetic acid now will lie backward. So these will react, these will combine. And when they combine, they will form back the acetic acid. So if that happens, that means the concentration of hydrogen ions will remain fair constant. Now, if that happens as well, the pH of the solution will remain constant. That is how the buffer solution can resist the change in pH when a small amount of hydrochloric acid is added into that system. So here, concentration that is number one. Number two, what will happen when a little amount of the strong base like sodium hydroxide is added to that buffer system? This is the question. Now let's see the mechanism. What will happen? Here in the solution, this one is already there, and also sodium acetate sodium ion. Now addition of sodium hydroxide, which is also a strong base, will ionize completely, producing the sodium ion and hydroxide ion. Now addition of hydroxide ion in the solution will combine with this hydrogen ion. This one will combine. And when they combine, they will form water. So hydrogen ion will combine with hydroxyl ion. Hydroxyl ion and hydrogen ion will combine together. This one will form water. Now if that happens, that means the concentration of hydrogen ion in the solution will decrease. If it will decrease, the pH will rise. Now in order to prevent that rise in pH, what will happen? Immediately the acetic acid will dissociate in order to produce more hydrogen ion to compensate for those hydrogen ion which have been used to combine with hydroxide ion from the strong base to form water. So if that will happen, therefore, the hydrogen ion that will be released by this acetic acid will be fairly constant, and automatically the pH of the solution also will be constant. Therefore, here now, my dear student, this is how the acidic buffer solution will resist the change in the pH because of the shifting of the position of the equilibrium, as you can see. So in that way, automatically the pH of the system will remain constant. So after we have discussed about the mechanism, and it is very important to remember this mechanism because sometimes you can be asked to explain the mechanism of acidic buffer solution. So you follow these steps. Now from there, we can have the equations on how to calculate the pH of the solution. It is very important how to calculate the pH of the solution. So let's see that equation. This is called the pH equation. Now consider this system. Consider that acidic buffer solution. Now let's take the acetic acid. If we write the ionization constant for the acid, Ka, I'm sure that you are able to, if I tell you to write that constant, you can be able to write it. The ionization constant for the acid will be the product of the concentration of the products divided by the concentration of the reactant. So it is very simple, as you can see. The concentration of the acetate ion multiplied by the concentration of hydrogen ion divided by the concentration of acetic acid. That is ionization constant for the acid. Now from there, our aim is to find the pH. Our aim is to find the pH of the solution. Therefore, we make this concentration of hydrogen ion the subject. What are we going to do? This one, you multiply that side. We are going to remain with this one. Concentration of hydrogen ion. So to remain with the concentration of hydrogen ion, that means you divide both sides this concentration of acetate ion. Now, the concentration of hydrogen ion will be is equal to ionization constant times concentration of acetic acid over concentration of acetate ion. Now from there you can introduce negative logarithm both sides. If you introduce negative logarithm both sides, you're going to have the following. So in this side, you're going to negative logarithm of hydrogen ion concentration equals to, here, negative logarithm, bracket, That one. So it is very simple. Now you can open the bracket. When you multiply in terms of logarithm, that means with plus. And this division, that means minus. So here we're going to have the following. Is equal to negative logarithm of Ka plus negative logarithm of concentration of acetic acid, and this division will be minus negative logarithm of acetate ion. That one. So it is very simple for you to understand this very simple simplification. So here, negative logarithm of hydrogen ion concentration, I hope that you understand, this is all about pH. And when we talk about negative logarithm of Ka, this is pKa, because this number Ka is very small. So in order to deal with large numbers, we get this one, pKa. So we can substitute these values into the equation there. When we substitute, you're going to get, instead of writing negative logarithm of hydrogen concentration, we write the pH. Instead of writing negative logarithm of K, we write the pKa. Then we proceed with the others. Because this one will be plus, we take this positive value into this side. So plus of acetate ion, then minus this one, negative logarithm of acetic acid concentration. Now, I think you know the mechanism of logarithm. If we minus, that means we can divide it there. And the bases are the same. So automatically here, we are going to have this equation. That one. So this equation can be used to find the pH of the solution. It is the pH equation for the acidic buffer solution. And it is called, also it is called Henderson and Hasselbalch equation. And it is used when the ratio of the acid and the salt are in 1:1 ratio only. So it is very important when you are making calculation to use this equation. Now, because these acetate ions, they are coming in the solution, they are coming from the strong salt and the weak acid. But because the strong salt produces many of them, so we consider these ones as the salt, concentration of the salt. So sometimes it can be written this way. That one is very simple for you. Now, my dear students, we'll be back after a short break. Stay tuned. Now, welcome back, my dear students. I can ask you the question. We have discussed about the acidic buffer solution. And the component of the acidic buffer solution, we have the weak acid and the strong salt of that acid, weak acid. Now, if I ask you what is the role of the weak acid in the buffer system, what are you going to tell? It is very simple. Now, the weak acids will provide a dynamic reversible system that will sense the change in the concentration of the hydrogen ion. And this will enable the equilibrium to shift accordingly, either forward or backward, depending on the disturbance that is made. So in that way, the hydrogen ion concentration will be balanced so as to balance the pH of the solution. So that is the role. It is important for you to remember that one. Now, my dear students, also if I ask you to give the rule of the sodium acetate, what are you going to say? It is very simple. We have seen in the mechanism. Sodium acetate, its function is to produce enough acetate ions which will combine with hydrogen ions from the strong mineral acid, which is hydrochloric acid, added into the buffer system. So it is important for you to remember those two rules. Now, it is our right time now to go to see some model questions so that we can use the knowledge that you obtain from this particular presentation to solve them and to see how some questions are coming from this particular presentation. Now, let's go to see the questions the way they are coming. Now, here, the first question says, acetic acid sodium acetate buffer solution containing 1 molar of the acid has the pH of 4.74 and ionization constant for this acid is 1.8 times 10 raised to -5. Now, what will be the concentration of the salt in the buffer solution? That is number 1. Number 2, the pH of the buffer solution if 0.01 molar hydrochloric acid is added. But number 3, the pH if 0.01 molar sodium hydroxide is added. So this is the question. Now, this question is also very simple. There is no problem. You can solve it as follows. Let's be together to solve this problem. Now, question number 1A, you are told to find the concentration of the salt. Now, what are you given? From the question there, we are given the following. We are given the pH of the solution. The pH of the solution that we are given from the question is 4.74. That is the pH of the solution. What else are we given? We are given the Ka, ionization constant for the acid, which is 1.8 times 10 raised to -5. That we are given. We are also given the concentration of the acid, which is 1 molar. So these are the data that we are given. What are we required to find? Required concentration of the salt. For part A, calculate the concentration of the salt. Now, do you remember the pH equation for the acidic buffer solution? Yes, here it is. Now that one. Now from there, because we have pKa and this is Ka, and you know that the formula of finding for pKa is equal to negative logarithm of Ka. Therefore, pKa there would be equal to negative logarithm of this value. 1.8 times 10 raised to -5. So you can use your calculator. You take your calculator, then you find that one. There you're going to get the following answer. You're going to get is equal to 4.7447. This is pKa. Now we just put it there. pH 4.74. pKa 4.7447 plus log concentration of the salt, that is what we're looking for. Concentration of the acid is 1. So you can take this one and subtract to this side. So 4.74 minus 4.7447 is equal to a log concentration of the salt. Now you can subtract it there. When you take your calculator, 4.74 minus 4.7447 would be equals to negative 4.7 times 10 raised to -3. Now, to get the concentration of the salt, you inverse the logarithm. So log inverse of this to negative 4.7 times 10 raised to -3 equals to concentration of the salt. Now you take your calculator, inverse logarithm of the answer. You are going to get the following. Will be equal to 0.9892 molar. So this is the concentration of the salt. That is number one. Now coming to B. Now question number 1B says the pH of the buffer solution if 0.01 molar hydrochloric acid is added. That is also very simple that we can discuss here together. But to discuss that one, we need to go back to the buffer system that we have the acetic acid, this one, which ionizes partially to give the acetate ion and hydrogen ion. We have also the sodium acetate, which ionizes completely to give the acetate ion and sodium ion. Now from there, hydrochloric acid is added. When it is added, it ionizes completely to give hydrogen ions and the chloride ions. As we have said that these ions, this one, will combine with this one to give this acetic acid. So there we are going to have the new concentration. The effect of adding hydrochloric acid will cause the concentration of the acetic acid to increase because it is the one which will be formed. Now, new concentration of the acetic acid. The concentration of acetic acid will increase by the same factor of the acid which is added. So originally here we had 1 mole. And here we have 1. The concentration of the salt which we have found here is equal to 0.9892 molar. So the concentration of the acid will be 1 plus the concentration of the acid which is added because it is formed here. So the concentration that is formed there is 0.01 molar. That is what is added. So there we are going to obtain 1.01 molar. That will be the new concentration of the acid. How about the concentration of the salt? Concentration of the salt here. Now, this is the salt, acetate ion. Because it will be used to combine to produce the acetic acid, that means it will be decreased by the same factor of the acid which is added. So, if originally we had 0.9892, that means this will decrease by the amount of that is added because they have been combined to make the acetic acid. So we subtract with that amount of acid which is added, 0.01. What are we going to get? Now we can use your calculator there. 0.9892 minus 0.01. You're going to get 0.9792 molar. That is the answer. So you have the new concentration of the salt, new concentration of the acid. You use your pH equation to find the new pH. Now pH would be equal to pKa plus log concentration of the salt over concentration of the acid. pH would be equal to pKa. We have already taken the value which is here, 4.7447 plus log concentration of the salt, the value is here, 0.9792 molar. Concentration of the acid, the new value is there, 1.01 molar. Now from there you can use your calculator to make simple calculation. Divided by 0, 1.01, logarithm of the answer. Now you take 4.7447 plus the answer. Here we are going to get the pH of this solution. The new pH will be equal to 4.73. This is the new pH of the solution. So as you can see there, it is very simple for you to do those calculations. The problem which is disturbing most of the students is to see which concentration will increase and which will decrease. So we have discussed this concept together, and I'm sure that you will be confident in answering these problems. Now, part C. Part C says pH if 0.01 molar sodium hydroxide is added. What will be the pH of this solution? Now here also it is very simple. You can solve that one. See, you are given sodium hydroxide, which is equal to 0.01 molar. Now you go back to your system, buffer system. This one will ionize partially to produce the acetate ion and hydrogen ion. The acetate ion, sodium acetate, will decompose completely to give the acetate ion and the sodium ion. And the sodium hydroxide here is added. When it will be added, it will produce sodium ion and hydroxide ion. So this one will combine together. These will combine together. When they combine, they form water. That means the concentration of the hydrogen ion will decrease. Now what will happen? New concentration of the acid. Originally we had 1. For the salt, 0.9892 molar originally. Now because the acetic acid will dissociate to compensate for these hydrogen ions, that means this will decrease. Will decrease by how? By what factor? By this factor of the base which is added. And this salt, because it will be formed, now this concentration will also increase by the same factor which is added from the base. So new concentration will be 1 for the acid. You subtract with that one, 0.01. You get, when you take a calculator, 1 minus 0.01. Now you will get 0.99 molar. For the salt, this one originally is 0.9892. Now here you plus with the amount that is added, 0.01. 0.9892 plus 0.01. You're going to get 0.9992 molar. So these are the new concentrations that you're going to obtain. So you can use your equation. pH is equal to pKa plus logarithm concentration of the salt over concentration of the acid. The value pH is equal to pKa. We have already obtained the value. The value is 4.7447 plus log concentration of the salt is that one, 0.9992 mole over 0.99 molar. So use your calculator to make that simple calculation there. 0.9992 divided by 0.99, logarithm of the answer is that one. Now 4.7447. Now when you use your calculator, you're going to get the pH will be equal to 4.74749. This will be the pH. There is no significant change in the pH. It's almost fairly constant. So this is how we can solve for these problems. Now from there, we can go to question number 2. It is very simple. Now question number 2 says, calculate the number of grams of sodium acetate which must be added to 500 centimeter cubic of 0.120 molar acetic acid to give a buffer solution of pH 4.6, assuming that the volume of the liquid remains unchanged, and you are given the ionization constant for the acetic acid is 1.8 times 10 raised to negative 5. I think I can guide you how to solve this problem. It is also very simple. When you want to solve this problem, you are told to calculate the number of grams of sodium acetate. That means you are finding for mass. You find it for the mass. Now what are you going to do to find it for the mass? Which must be added to 500 centimeter cubic. Now, to guide you here, we have the concentration of the acetic acid. When you want to use the pH equation to find this problem, you have first to find the concentration of the salt from the equation. If you find the concentration of the salt, you have the concentration of the acid. You can use that one. You have the pH, and you have the Ka. So this Ka should be changed into pKa. To change to pKa, you go to negative logarithm of this value. You get that value of pKa. So you put those data in the pH equation. After you find the concentration, therefore, you come to the formula which says the concentration, that is molar concentration, is equal to number of mole over volume. So you look for the number of mole. Number of mole there can be obtained by taking the concentration that is obtained from that equation and the volume. The volume is 500 centimeter cubic. You convert this 500 centimeter cubic into decimeter cubic. That means you divide by 1000. You get 0.5 decimeter cubic. So after you get the number of moles, it is very simple now. You can recall the formula. Number of moles is equal to mass over molar mass. So you make the subject mass. Therefore, mass will be equal to number of moles that you obtained times the molar mass of the sodium acetate, which is equal to 82 grams per mole. You get the mass that is needed. So this equation is very simple. You can solve it. Now, can you do it? Take a piece of paper and try to solve this problem. Now, let's see the question number 3. This is another form where question might come. Given a buffer solution containing equal concentrations of acetic acid and sodium acetate, what will be the effect on the concentration of acetic acid, hydronium ion, and acetate ion when the followings are added to it? Hydrochloric acid and potassium hydroxide. This equation is also very simple. Why? Because we have discussed the mechanism of the acidic buffer solution. When you add, for example, hydrochloric acid, it will give the hydrogen ion. That hydrogen ions will increase the concentration of it, making to lower the pH. So what will happen is there? The acetate ions from sodium acetate will react with it to form acetic acid. So the concentration of the acetic acid will increase. And as you can see with these examples on the board here, we are just adding the concentration of the acetic acid will increase by the same factor of that acid which is added. And how about the acetate ion? The acetate ion will decrease because they will be used to form the acetic acid. Will decrease by what amount? By the same amount that is added. And the concentration of hydrogen ion will be very constant. So it is very simple. And also when you add potassium hydroxide, the same thing happens. It gives hydroxide ion. This hydroxide ion will combine with the hydrogen ion forming water. So we have seen that when this happens to this example here on the board, what will happen here? That means after combining, this acetate ion will ionize more to produce the hydrogen ion to compensate for its loss. Now, the concentration of the acetic acid will decrease because they will be used to produce more hydrogen ion. And the concentration of the acetate ion will increase by the same factor of that potassium hydroxide that is added. So it is very simple to answer those problems. You can take a piece of paper and try to write these questions and try to do it by yourself. So this topic, this presentation, I hope that was very interesting. And the buffer solution is very, very important. It is used to maintain life. For example, different biochemical processes, they need the pH buffer solution which maintains the pH. For example, the blood. The blood has got the pH which is close to 7.4 because it consists of the carbonate and bicarbonate buffer system. It is also used in brewery industry. For example, before fermentation, buffer solution is added in order to balance the pH, to make not to make the solution too much acidic. It can be used in baby's lotion. Why? Because the baby's lotion is there, the buffer solution is of about 6. Now that one will prevent the growth of bacteria in order to prevent the destruction of the diaper. It can be used in in textile industries for balancing the pH of different dyes. It can be used in laundry processes in balancing the pH. So buffer solutions are used in most part of our life. I hope that this presentation is very important. Hope to see you next time. Now, my dear students, thank you very much and have a good time.